Oui. Je peux le trouver. Passer au direct. Ça y est, je suis en direct.
Ah, tu te vois toi-même.
Voilà, je passe en direct.
Ah oui, j'ai l'ai ici.
Voilà, tu es en direct.
Voilà.
Ok, donc là, on est en direct, en YouTube.
Ouais, c'est mieux.
Et là, je suis en train de contrôler la diffusion.
Et tu l'as reçu, là, oui?
Ah ouais.
On peut lancer la réunion? Tu peux lancer?
Ouais.
Il dit comme ça, pour voir si... Ici, ça va.
Oui, j'ai l'écho.
Ok, super. Là c'est en direct.
J'ai l'écho de tous les trucs.
Tu as l'écho de tous les trucs?
Non, je m'écoute là-bas et
Ah merde, donc.
j'écoute les YouTube, mais c'est moi.
Ah oui, donc tous les bruits de la salle vont passer.
Mais pas mon par là. Je vais me voilà la toute par de mon temps.
Quand ils vont parler, du coup, le haut-parleur. Ça va être des échos?
Mais il faudrait que ce soit la machine, que ce soit le zoom, que Oscar aussi mette sa machine sur le zoom de la.
Tu passes mes slides?
Oui, là,
Ou alors il faudrait que tu branches, tu prennes le micro là.
Ça, c'est des échos.
En fait, le mieux, ce serait que vous repreniez la machine d'Oscar, que Oscar, quand il a fini, il lance le zoom de la délibération.
Ouais.
Et il sort. Quoi. Enfin, voilà, normalement, c'est pas très, pas très correct, mais enfin, bon.
De quoi?
Parce qu'il y aura des échos.
Pour avoir la même qualité de son pour la délibération.
Non, hier, ça marchait parfaitement. Ouais. On coupe les micros et partout. Et vous restez là dans l'ordi et on sort de la salle. Ouais, ça marche.
Comment tu coupes tout alors?
Ah, c'est facile. Là, on coupe les micros.
Quand tu partiras,
oui, part et tu fais un zoom ordinaire comme si c'était ta machine. Alors, je passe là les.
Ouais, merci.
Ok, là, par exemple, là, on part. Ok, je suis en train de présenter et ça passe en YouTube normalement. Tu es en train d'écouter en YouTube.
Oui, je t'écoute en
YouTube.
10 secondes de retard.
Oui. Donc, so hello everyone. Tac. You want to see the slides or not? Ça tac. À la limite, le deuxième écran, il n'y a pas besoin de le laisser juste pour contrôler en fait.
Ouais, c'est ça.
Donc il n'y a pas besoin de le laisser l'autre. Parce que ça ajoute un petit peu les décollages. Pour la discussion.
Ouais, mais ouais, c'est ça, pour la discussion, c'est bien. Moi, je serais toi, je laisserais de toute façon au début et à la fin. Après, pendant, c'est pas grave, hein, les gens ils vont s'habituer. Hein. Puis les gens ils bougeront plus.
C'est laisser là-bas quoi.
Moi, je serais toi, je laisserais le zoom.
Ah non, le zoom, c'est simplement le YouTube, c'est pour tester.
Oui.
Je laisse le zoom, c'est la fin. C'est pour que tu vois que tu as
le
YouTube. Ça marche.
Tu laisses ton
Ok. Mais là, je te laisse te connecter à ton ordi là-bas.
Ah oui, on laisse l'ordi là-bas.
Tu connectes ici et je connecte
ici. Comme on dit, oui, on fait la même chose demain, sauf que pour demain, au moment de choisir la caméra, plutôt que choisir la webcam, tu choisis l'autre.
Ah ouais,
mais c'est Zoom, on le fait sur Zoom sans problème.
Et je contrôle le streaming ici. Alors. Je contrôle là, je vois
le. D'accord. D'accord. Il n'y a rien à contrôler sur YouTube, non? Il y a des trucs à contrôler là?
Non, c'est juste arrêter la diffusion.
Arrêter la diffusion, c'est toi. Je pense que Carlos l'a fait hier.
Oui.
Non,
c'est Zoom c'est depuis Zoom que tu fais le streaming.
Oui, je suis sur Zoom. J'avais déjà programmé l'adresse. Et donc là, c'est automatiquement, ça passe. Okay. C'est ça que les gens sont.
Oui, parce que dans l'idéal, tu seras tout seul ici. On allume l'ordinateur là-bas, on
là
aujourd'hui, paf,
vous êtes tous les deux là.
On se met là-bas.
Moi, je serai là, moi.
On se met là-bas, oui.
Ouais, c'est ça.
Ou j'ai tout le temps, je vais me par ici pour cas où je contrôle la caméra, où j'ai la caméra. Pour la caméra, pour être plus proche.
Et voilà, et donc je passe les slides. Super. Oh, c'est bien. Tiens.
Après, YouTube a marché tout le temps. On n'a pas jamais eu de soucis de YouTube.
Non, YouTube, non. Non, le problème, c'est les bandwidth
Après, c'est tout aux jurys qui sont normalement pas besoin de faire un test Zoom. Ce Zoom, maintenant, il faut que tu renvoies l'invitation Zoom
à tout le monde. Après, est-ce que je vais tester les trucs?
Ah, il fallait des trucs de Zoom d'autoriser ou pas les gens.
Oui, je l'ai programmé automatiquement pour qu'ils rentrent.
Oui, d'accord. Par contre, les Zoom, c'est simplement les jurys, peut-être un professeur, para tout le public.
Okay.
Putain, ça me fout les boules de faire ces trucs techniques avec autant de... En fait, les bruits, ça venait du système Polycom.
Ouais, mais non, mais ça va bien se passer là. C'est simple, tu fais tout avec.
Mais si tu sors avec le PC de lui, tu vois comment ça marche. Sors dehors et écoute sur le PC. Je reste ici, je te parle. Okay. Comme ça, tu vois la qualité.
Oui, que déjà que les réseaux tombent. Ben là, je suis rassuré que les réseaux soient Ethernet, donc c'est super.
Ouais.
C'est stable,
Ouais.
parce que sur les réseaux Wi-Fi, ça se déconnecte, c'est assez stable.
Ouais.
Et que les mains qui appellent les helpdesk ici, ils ne savent pas quoi faire. Ils ne sont pas vraiment...
Ouais. Non, l'assistant technique, c'était même pas quelqu'un d'ici, non?
Non, je ne sais pas, il est à Paris ou je ne sais pas.
Personne, c'est chiant ça. Ouais.
C'est hyper chiant et c'est un système Polycom qui est censé être super moderne, mais ça pose des problèmes à tout le monde. Tous les gens qui sont en Macintosh, ça ne marche pas.
L'avenir, c'est de l'Ethernet, des trucs Zoom et des trucs comme ça.
Polycom, c'est hyper cher et demain, il faut que j'appelle pour annuler la réunion. Annuler la réunion Polycom visioconférence. Et on va passer sur le système Zoom, c'est un peu.
Ouais, tu leur dis, non, on annule le Polycom, on va passer au Zoom. Ah, oui, non. Ça coûte très cher.
Il y a du café dans le sol, non? Il n'y a pas de café,
Ah, dehors, je pense que oui, qu'il a une machine. Oui.
Ça va, niños?
Allô? ¿Tú m'entends? Allô, probando. 1, 2, 3.
Oui, 4. Super. Voilà, ça marche très bien.
2, 3. ¿Tú m'entends bien?
Oui, et vous nous entendez? Ouais, normalement, oui. Oui, super. Super, on t'entend.
Allô?
Oui, génial. Super.
Ah, j'écoute mes haut-parleurs de l'autre côté. Ah, ils sont restés. Oscar, tu m'entends?
Oui, super, je vous entends très bien.
Voilà. J'ai une question sur la slide 12B.
Sur la slide 247.
Les unités, je ne suis pas d'accord avec les unités. Enfin, je ne comprends pas. Ah, par contre, on ne t'écoute pas ici, Oscar.
Ah bon? Vous ne m'entendez pas? Vous m'entendez? Si je parle, vous m'entendez?
Les retours sont, oui.
Je parle, je suis en train de parler, je parle.
C'est le PC de...
Ah, je parle. Ah, est-ce que le micro est coupé? Non, j'ai mon micro. Et je parle. Est-ce que vous m'entendez?
Je ne vois pas. Qu'est-ce que j'ai fait? Non, je vois le contrôle de réunion, mais je n'écoute pas Oscar.
Ah bon, alors.
Je vais chercher Oscar.
Oui.
Alors.
C'est plutôt. Mais normalement, le micro, il est allumé chez toi.
Oui, il est allumé.
Non, je n'entends pas Oscar parler. Ouais. Est-ce que ça vient de c'est ça que je pense? Ça marchait.
Regardez quoi?
Je sais pas.
Ah non, peut-être ici.
Voilà. Est-ce que vous m'entendez? Non, mon micro a l'air de marcher. Hein.
Non, on t'entend pas.
Mon téléphone, mais
on t'entend pas.
Moi, mon micro est
Tout à
ouvert.
l'heure, on l'entendait. C'est pas le système là qui on a appuyé un truc.
1, 2, 1, 2, 1, 2. 1, 2, 1, 2, 1, 2.
Ah, des
1, 2, 1, 2.
Avec qui?
1, 2, 1, 2, 1, 2.
Oui, avant, c'était le truc Polycom.
Ah oui,
oui,
comme...
oui. Oui. Coupez mon audio.
1, 2, 1, 2. 1, 2, 1, 2, 1, 2.
Et, si je fais, par exemple, Google.
Mais parfois, avec Zoom, il faut bien configurer les entrées et les sorties de son avant de lancer Zoom. Je ne sais pas si tu as redémarré Zoom.
Tout à l'heure, tu m'entendais? C'était dehors.
Ouais, tout à l'heure, c'était bien.
Il y a un truc qui a changé.
Et donc, en même temps?
Non, on entend bien le micro, mais c'est vous qui n'avez pas votre micro.
Oui, oui.
Ah oui, 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 oui.
Je suis connecté aussi sur le téléphone.
Et là, on n'entend pas.
Je devrais parler.
Bernard Helou. C'est qui Bernard Helou?
Attends, c'est...
Oh, c'est moi. J'ai déjà préparé les trucs pour Bernard.
Qu'est-ce qu'il fait, Bernard?
Ah non, c'est moi, j'ai mis mon nom. Allô? Allô?
Ah, mais ça marche pas.
Allô?
C'était dehors, on t'entendait pas, hein?
Ah, vous m'entendiez pas tout à l'heure?
Non.
J'arrête. Les YouTube est comme ça, Miguel, pour voir qu'est-ce qui se passe. J'arrête et je relance Zoom.
Ouais.
Ah.
Allô? Ahí la otra persona que se conecta, ¿no?
Si, c'est Laura. C'est Laura Chela.
Allô, vous m'entendez là?
Non, on ne t'entend pas.
Oh, mais je l'entends.
Tu entends qui?
Fabrice? Fabrice, oui.
Ah ben, on n'entend pas. C'est ici, on n'entend pas.
Et le son ne reprend pas
Dans
dans
la
la
salle, on n'entend pas. Alors, c'est ça le souci.
Le-
Ah, peut-être que c'est dans la console.
Non, non, à mon avis, c'est sur ton portable. Il renvoie pas, à la box, à la Conftel.
Alors, tu parles, Fabrice, a ver.
Ah, ouais, je parle là.
Ah, maintenant, on t'écoute, oui.
C'était quoi?
1, 2, 1, 2. Vous m'entendez?
Oui.
Vous m'entendez bien?
Oui, très bien. C'était
Ah bah,
quoi?
c'est bon, alors.
C'était quoi les soucis?
Je sais pas. J'ai fait les tests de son encore.
Alors, vas-y.
1, 2, 1, 2.
Comment tu as fait les tests son?
Non, non, les tests sont, tu viens sur le micro.
Alors voilà, j'ai plein de questions.
Tests sont, oui.
J'ai plein de questions que je dois pas poser, tellement j'en ai.
Le micro.
Ma première question, c'est est-ce que vous m'entendez?
Oui, la première question. Je vais repartager mon écran. Ok, je partage mon écran. Je vais relancer la présentation.
Ouais.
Écran 2, diaporama. Voilà, partagé. Et voilà.
Et alors, ma deuxième question, c'est est-ce que vous m'entendez toujours?
Oui, on t'entend toujours.
Bon, bah alors, c'est pas le partage d'écran qui gêne.
Qu'est-ce qu'il y avait qui marchait pas?
Bon,
Je sais
là.
pas, normalement, on l'avait configuré tout début.
Voilà. Bon, bah c'est pas mal alors.
Oui, mais si. Alors.
Si on met une caméra comme ça, tu vois, on te voit bien, complet.
Qu'est-ce qu'il est ça?
Ah oui, il y a une caméra en plus là.
Oui, il y a Laura qui se connecte, ou David. David, c'est le fils de Laura qui va être en train. Hello, David, or hello, Laura. We are connected. Can you listen to us? Ciao, David, o ciao, Laura. Can you plug your micro?
Hein? Tu poses une question?
Oui, à David. David.
Mais si on écoute Fabrice, si Fabrice t'écoute, c'est pas.
Ah, bah c'est fini après.
Ah si, il y a quelqu'un qui.
Ah, il y a quelqu'un.
David? Ah non.
Donc c'est peut-être ton micro qui est passé quoi?
C'est mon écran qui passait.
Non, son micro à elle. C'est peut-être pas assez fort. Oui, il a pas mis son micro.
Oui. Ah, pardon, c'est moi, c'est moi.
Il a pas mis son micro là.
I am here.
On l'entend pas, David. Fabrice, tu entends? Tu entends?
Moi j'entends tout, ouais.
Et tu entends? I can hear you, I can see. Ok, David. David, il peut voir, mais il peut pas. Can you speak, please? Can you...
Ah, c'est bizarre parce que moi j'entends. Hein.
Mais tu entends l'autre personne?
Non, je t'entends toi.
Mais et l'autre personne, tu l'entends pas?
Non, j'entends pas David. Et là, pour le coup, c'est un problème chez David alors.
Oui.
Et puis c'est curieux, je pense on voit pas si son micro est ouvert ou fermé.
Et il est ouvert.
C'est vrai que normalement.
Et sa session s'affiche pas.
Si, elle est activée.
Chat, ok. Ouais, c'est bizarre.
Can you open your micro?
Ouais, mais peut-être qu'il devrait activer sa caméra pour voir si la vidéo ça passe. Ouais, c'est très étonnant ça. Oh.
Alors. 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 Allô. Allô.
Si je me déconnecté ma session Zoom, tu es déconnecté? Je vais essayer de me déconnecter ma session Zoom.
Mais si tu déconnectes, je ne sais pas. Oui, d'accord, on continue.
Je peux te nommer comme co-animateur, en fait. Nommer comme co-animateur.
Okay.
Et si je me déconnecte, ah, connexion.
Ça, c'est le YouTube.
Ça, c'est des... Non, ça, c'est... Toi, tu es coordonnateur. Tu coordonnes la session. Je partage mon vidéo. Et... Ah, comment on fait? Attends, je vais me connecter avec mon téléphone. Laura Cella. Ah, hello, Laura. I'm trying to... Hello, Laura. I can listen to you. Good.
Can you hear me?
Yes, yes, I can listen to you. That's great.
Gira, fammi vedere il monitor, non vedo. Yes, sì, sì. Okay, it works. It works. I can hear you, I can see you, and I can speak.
Ah, great. And can you see the presentation, my slides?
Yes, yes.
Great, it works. Fabrice, can you listen to me? Fabrice, tu peux entendre?
La presentazione, no?
Yes, perfect. So we are going to switch. Laura, I'm going to send you tomorrow another link, Zoom link, and we are going to do everything with Zoom.
Okay, thank you.
Scrivi, write an email to my mom.
Okay.
Scrivi, write an email.
It's okay.
Su.
Prego.
Sorry, 1 minute. I am scrolling.
Mama is in the car. Okay, no worries. Laura, it's okay. Perfect. Thank you very much. I think it's okay. I'm going to send you the Zoom link tonight for tomorrow's connection in internet, in Zoom only. We are going to give up with Polycom. We are going to switch to Zoom.
Okay, I can hear you. Write an email to my mom, okay?
Yes, I'm going to write an email to your mom. Thank you, David.
I have to exit.
Thank you, Laura. Bye. Thank you.
Bye. Thank you.
You can. Bye. Oui, demain je leur demande. Je pense qu'ils ont compris. C'est Costas qui a peut-être lu trop rapidement. Parfait. Non, je pense que c'est bon. Je pense qu'on a résolu les problèmes techniques.
La caméra, c'est...
Après, c'est les problèmes, c'est des sons. Non, elle s'est connectée depuis son téléphone.
Ouais.
Et c'est comme ça que j'ai pu la voir.
Oui, mais alors, demain, tu vas pas la...
Elle s'est connectée depuis son téléphone, ça a marché depuis son téléphone. J'étais connecté à son téléphone.
Et c'est pareil, par exemple, je me connecte depuis mon téléphone.
Ouais. Mais pourquoi elle n'entendait pas parler de nous?
Parce qu'en fait, elle a dit à son fils comment se connecter. Alors, si je me connecte ici.
Oui, j'étais connecté à mon téléphone aussi. Seulement que pour les micros, c'est compliqué. Voilà. Je coupe le micro pour éviter.
Ok.
Ah, tu vois. C'est mon téléphone ici.
Non, mais demain, on va commencer à faire les tests à 13h.
Non, c'est mon téléphone. C'est mon téléphone quand on m'a dit d'activer le son, mais c'est le téléphone, c'est pas là ici. C'est le retour de son, de tout. Non, mais c'est bien, tu vois, je laisse l'ordinateur comme ça.
Oui. Et ça annule l'écho, les échos des systèmes.
Oui, tu parles bien et tout le monde t'écoute.
Donc c'est un système spécial.
Le micro était allumé et tu parlais à la salle.
Ok, très bien.
Non, c'est bien. Après, c'est que les seuls tests que peut-être on fait demain,
Oui.
Y la de desextensión, 2 micros pequeños que trae para que la sala sea más larga. Si yo te coloco un micro de esos pequeños y coloco el aparato aquí, si lo escuchamos mal, lo volvemos a poner aquí.
Vale.
De todas maneras, aquí funcionó con todo el mundo.
Ça marche.
Fíjate que Fabrice habló desde allá
Sí,
atrás
sí.
y te escucha.
Au cas où, je vais te donner la présentation dans ton PC et on switch sur ton PC.
Ah oui, au cas où, je pensais ça aussi. Au cas où, voilà.
Je passe là-bas.
Tu passes là-bas.
Ouais. Il faut que les choses techniques soient suffisamment résolues pour que les choses après, on soit tranquille. Ouais.
Non,
Okay.
parce que les pires des choses, s'il y a des échos, des trucs comme ça, c'est plutôt, ici dans la salle, c'est plutôt commencer par éteindre les micros ici.
Okay.
Les micros, mais normalement, on a bien de faire le test, ça marche bien. Ça marche bien. Les gens, tout le monde restait. Quand vous parlez les trois comme ça, Fabrice là-bas, ça s'entend bien, un petit truc. Oui. Mais de toute façon, normalement, c'est une seule personne qui parle à la fois.
Ok. Bon.
Oh, ça va bien?
Super, Fabrice. Tu entends bien? On t'entend très bien
Ouais,
ici.
c'est impeccable.
Dernière test.
Et là, je vais montrer à Mireille les slides et pour voir qu'est-ce qu'il pense.
Ok.
Le président, avant le président. Et...
Bon, bah, je redescends avec vous alors.
Super. Comment? Oui, mais ce qui m'inquiète, c'est mes enfants qui sont dehors. Et... Oui, ils sont là. Là, en train de jouer, en train de faire des dessins, et il y a ma fille qui est là. Oui, dans le hall. Oui. Et demain, ils sont là, ils sont dans la salle aussi.
Alors, demain, il faudra se méfier pour l'accès, mais Mahmoud.
C'est pas mal ça.
Voilà.
Mahmoud qui est dans les.
La dernière test, c'est voir s'il y a des échos, mais non, normalement.
Ah ben, j'ai. Mais bon, s'il n'y a pas d'écho ici.
S'il n'y a pas d'écho, oui.
Et normalement, les YouTube continuent à marcher. Hein. Oui, bah, très bien. Bah, je vais peut-être éliminer si ça merdouille.
La seule chose, c'est que c'est le micro. Vous pourrez mettre le micro.
Ah ben, et je continue à diffuser sur YouTube. Hein. Je suis en train de me voir ce qu'ils sont en train de diffuser sur YouTube.
Pour l'accès à la salle, il y a Mahmoud Hassan qui a un bureau ici pour sa start-up. Et j'ai vu un de tes arts, là, je ne sais plus comment il s'appelle. Et c'est lui qui m'a ouvert. Donc, éventuellement, il faudrait le contacter pour, au cas où, au moins prendre ses coordonnées pour, au cas où, ouvrir la porte d'entrée. Là, parce que ce matin, c'était fermé. Comment t'es rentré, toi? Ah oui, il y avait quelque chose qui
C'est ça que les gens font.
Okay, ouais.
Non, mais à la réunion que tu as programmée demain, tu as l'accès à la salle et tout ça, les codes.
À la salle, oui, mais pas au bâtiment.
Oui, il y a un double code. Dans
le bâtiment? Fabrice, il n'a pas trouvé?
Parce que Fabrice n'avait pas la...
Non, je l'ai envoyé à Fabrice. Tu n'as pas pu rentrer
oui,
dans
c'était bizarre.
dans le bâtiment?
Oui, c'était pas bien.
Il ouvre la porte ici, mais ça ouvre
non,
pas les bâtiments.
il a un code / un autre code. Mais quand tu l'as envoyé à Fabrice en texte brut, c'était pas dans les jolis formats.
Non, mais la porte principale, il n'y a pas de code.
La porte del bâtiment.
Ah non, mais il y a une porte ici, de ce côté-là de la porte. Il y a une porte ici, de côté. C'est l'écho de la porte ici.
Voilà, je vais essayer. Ok. Bon, je te montre Mireille vite fait, si tu veux. Comment? Non, mais c'est un peu, je sais pas. Non, parce que je ne suis pas prêt du tout. Donc, elle est juste parler un petit peu sur la structure, rapidement. Donc, je me présente. That is the structure of the presentation, covering different aspects. First, my CV. So I start I'm going to see how much time I spend in browsing all these slides, just to see. So I'm an electrical engineer and a master's in biomedical engineering from the University of Andes in Colombia in 1998. I'm going to have everything here, I guess. I perform an internship in Telecom Bretagne in 1998, and after some back and forth between Colombia and Colombia and France. I completed a PhD in the Université RNA and the TSC, the same lab, in 2004. After, I went to Australia in 2005 to first start as a postdoctoral fellow in Sydney, then I continue as a research scientist between 2005 and 2009 in Brisbane, where I worked in development of matched biomarkers for Alzheimer's disease, to take a position here in France as associate professor at the University of Rennes, one where I work mainly in signal and image processing, teaching activities in signal and image processing, computer vision, computer science, mathematical tools for engineers. And mainly, I've been the coordinator of the Masters in Electronics, Electrical Engineering, Control Systems between 2017 and 2021. My research activities have been developed at the TSI, the Laboratoire de Traitement de Signal de l'Image, and the team Impact, and in strong collaboration with the Centre de Jean-Marquis. There have been around exploitation of multimodal data for prediction of response to radiation therapy, mainly toxicity and recurrence, around prostate cancer, which is the work I'm going to present today, which is around this pathology. So to start with the clinical context, prostate cancer is the most common type of male cancer in the developed countries. In France, it reached 65,000 cases and almost 10,000 deaths. Roughly 1 out of 6 men will be diagnosed with prostate cancer. And what is important to highlight here is the prostate is this gland located here that has both a urinary and sexual function, and is surrounded by the bladder, the urethra, and the rectum. Once the prostate cancer is diagnosed via digital rectal examination or PSA levels or even histology, and the clinical scan performed, different therapies are possible. Either we go to local treatment or systemic. Local it means that it's only to find a tumor where the different options are available, like surgery, radiotherapy, HIFU, focalized ultrasound. And when we're speaking about systemic, it can be chemotherapy or more chemotherapy. We are focused here in this work mainly radiotherapy, whose interest is the preservation of the organ and is indicated mainly in localized tumors. It can be used also as a secondary treatment. Two kinds of radiotherapy are possible, either external beam radiotherapy using external beams, or radiotherapy where some needles are inserted in the post-prostate. The main focus of my work has been in external radiotherapy, which consists in the use of radiation applied from the exterior of the body with an accelerator in order to destroy malignant cells. And this is used based on a dose distribution. This distribution is planned beforehand, and the idea is to maximize the dose when these beams intersect, delivering a certain amount of dose. Well, the treatment of radiotherapy consists in two main steps. The first one is the planning, and the second one is the irradiation. In the planning, the first step is to take a CT scan, where the patient is all the structures of the patients are delineated, mainly the prostate, which is the target. We define a margins surrounding the prostate, called the prostate target volume, and the rectum. Merci Fabrice, merci Miguel. Qu'est-ce que j'ai fait? Je l'ai mis dans ma voiture. Ok. Il y a quelques bouteilles de vin dans la voiture aussi. Il y a quelques bouteilles de...
Gardez pour demain.
Oui, et je vais amener des empanadas.
Ah, super.
Voilà. Hey, merci beaucoup. Hein. Je ne sais pas ce que je fais. On est en panique. C'est vrai que les gars qui est là, sont en panique. So the rectum. So the organs are delineated, and based on this delineation, a dose is computed to meet or to reach or to fulfill some clinical requirements. These requirements are based on well, the idea is to simulate and propose the configuration for the beams, and it should be validated by an integration oncologist based on this optimization on the dose volume histogram. I want to explain what is dose volume histogram. Actually, the dose volume histogram is a graph that represents for a whole organ the amount of dose that is delivered, the percentage of the organ that receives at least a certain amount of dose. Here in the prostate, for example, the idea is to maximize the dose received by the prostate. So that's why you have this constraint, which is that 95% of the PTV should be irradiated with at least 95% of the prescribed dose. Unlike the prostate, in the organs at risk, the idea is different. The idea is to minimize the percentage of the organ that receives a certain amount of dose. Very usually, we follow some recommendation, and in this case, the recommendation, we can see that the maximal dose can be, for example, less than 76 gray, or, for example, that the irradiated volume at 72 grays must be less than 25%. So basically, in this constant, the plan is approved, and then in the second step, the dose is irradiated to the patient. And so the patient is located in the accelerator via some localization system, either tattoos or CBCT, and then the dose is delivered. This delivered dose can be performed using intensity modulated radiotherapy system, IMRT, which is very common today, as opposed to conformational radiotherapy before. And there are more and more performance systems which are able to deliver a correct amount of dose, like CyberKnife, or even today the emergency of the MRI Linac. And this dose is applied not only in one fraction, it's applied in several fractions. Typically in the prostate, we are thinking about applying 2 grays per fraction, reaching 80 grays in a typical protocol with 40 fractions. But the trend today is go towards hyperfractionation in terms of increasing the gray and decreasing the number of fractions. So as a conclusion of this part, the idea in external radiation therapy is to maximize the dose when the beams intersect, I mean the prostate, and minimizing the dose to the organs at risk surrounding the prostate in order to diminish the secondary risk. So it's a compromise, a trade-off between the local control and the secondary effects. The secondary effects can be affect the sexual function, the urinary toxicity, the rectal toxicity, which can be higher in some cases. It can reach more than 20% of the cases. And in terms of recurrency, this can be up to 30 or 40% in the population of high risk. So the idea in the works that we have been developing this last year is first to predict these events, predict the toxicity, predict the recurrence, and in order to improve the radiotherapy, going through a personalized plan. This planning, of course, requires also the description, a precise description of the target and organs at risk. This in a context of technological developments. We see steadily increasing the number of data, the amount of data available, not only imaging, but also accelerators like MRI Linac, computational methods as well. So this work of personalized planning, the objective of these works in the last year has been to develop methods to personalize the planning. And I try to split into main axes. First axis will be the prediction of both toxicity and recurrence. And the second one is how to improve the target, how to define better, how to achieve a better definition of the target via, for example, the implementation of the use of MRI. Everything in a flood of data, we have as an input data going through all the workflow in radiotherapy, namely biological tests, digital distribution, imaging, even histopathology. And not only the data, but also to exploit the data as well as the knowledge that we can produce from observation from experiments before. And the idea is the methods that have been developed been as trying to answer to these two questions. First, how to exploit all this data in order to answer to the question of toxicity and recurrence targeting, and how to introduce knowledge in order to support all these decisions of personalized. So the methods can be split in these three different boxes. The first one part is around toxicity, and namely the classical NTCP models, the machine learning models, voxel-based analysis. The second contribution will have been around the implementation of the radiomics workflow in response to the problem of recurrence. The model-based prediction based on in silico simulation. And the third point will be the multiple model fusion and the generation of synthetic CT in order to improve the target. So to start with the prediction of toxicity, what we might say is that the idea is to go through the full exploitation of 3D dot distribution in order to answer the problem of when toxicity happens and how it happens. And this is a very complicated problem. In the literature, what we have found before is that the way in which the data is exploited is through those volume histograms that I explained before. So because it's a reduced signal that is monodimensional, and the traditional models before trying to understand, to explain the toxicity by considering the whole organ and express in a sigmoid function the probability of having complication, having toxicity in function of the dose. So the idea was before to try to figure out from a population data set, which was to fit some parameters and to fit the curve and saying that for a given population, we have a probability of having toxicity based on the equivalent dose of the whole. New approaches have been appearing in the last year, getting around these NTCP models, going to machine learning techniques. And here we appears the first contribution of our work in 2010 or 2012. It was with the first PhD student that arrived to the lab in this team. It was Juan David Ospina, who proposed original machine learning methods using random forests indeed by exploiting the volume histogram, as well as Vargas in an inter-team work with the CESAM team to propose to use the expertise developed in the lab as in methods of independent component analysis in order to explain also toxicity, showing that it's it can be an improvement in the prediction using these machine learning methods. And the problem with these methods is that the relationship that between the spatial distribution, which was the origin of the motivation, is lost. There is no relationship between the spatial distribution and the toxicity. So in response to that, the literature is some extent, some of the problems of the dose histogram is of course is a reduced representation of the 3D plane dose. Then in reality, the toxicity doesn't involve a single organ. It can involve several structures at different spatial scales. And another problem is a DVH, because it's a reduced version of the 3D dot distribution. So different 3D dot distribution may lead to the same DVH. Also, the information on spatial distribution, of course, is lost. But mainly that the local correlation between the small portions of the organs and the toxicity is not well established. And so to get around these problems, what we have found in the literature is that some teams have split for example, the rectum in some small substructures, and they reproduce the analysis using small deviations or deviations from small portions of the rectum. But this is not enough because the spatial distribution is lost. So other approaches have used this concept of those surface maps, which idea is to represent in a plane, in a 2D plane, the dose to the surface. And then afterwards, perform kind of pixel-wise analysis of comparing the dose in this surface to end up having these cartographies representing, for example, the places where this average between the population with toxicity or not toxicity is statistically significant. And this, however, is limited to organ surfaces. There are some issues with volumes and does not take into account multiple structure involvement. So our contribution here to trying to answer to this problem was to propose for the first time the use of dose volume maps to perform voxel-wise analysis. Although this idea was proposed before in neuroimaging, our idea was to split the population into groups, population with toxicity that was explored in the Gael-Drian's PhD, and to have an anatomical template which will be the common coordinate system to perform an inter-individual mapping via 3D registration and to represent the dose in this common system. So each one of the voxels of two different populations in the same coordinate system will be anatomically equivalent, so the dose can be compared. And so we proposed for that a 3D voxel-based workflow. So we have the population data, we have a template via spatial normalization, and in our case was non-rigid registration. So we perform non-registration between each of the patient and the template. We get a deformation field. This deformation field is then applied to the dose. So we have a deformed dose in the common system, and this is performed for all the patients. So by doing so, we have this workflow, and at the end, we can perform voxel-wise analysis. This voxel-wise analysis can be either a test, Wilcoxon test, or different statistical tests that allows us to highlight regions where this heterogeneity in the dose can appear. So in that way, we proposed it in 2013 this seminal paper, which has been highly cited, which is the use of voxel-based analysis of those based on this non-rigid registration concept. So as you can see here, we can represent the cartography, representing the difference between the two populations, and this small small group of voxels here represent the region where these differences are statistically significant. So in that way, we can highlight and propose to suggest that there are some part of the rectum that can be more sensitive to irradiation. So this first study was covered with a reduced number of patients. We didn't optimize the registration method. We knew that there was a large inter-individual variability, and the improvement of the prediction was not demonstrated. So with the same population, we tested in the cases of Navidospina and Aurelio, different ways of exploring performing voxel-wise analysis, but the problem registration was not solved yet. So in Gael-Drian's PhD, we tackled this problem of the individual variability, and we answered to the problem on the selection of the right common coordinate system. So he performed a nice study in which different rectums were clustered together in order to reproduce the voxel-wise analysis in different clusters. And we observed is that the subregions that are significantly different, 18 different templates, are different depending on the template. So to cope with that, we propose a customized registration method based on the rectum, customized photo rectum, in which we describe the rectum via the Laplacian distance map, which is a normalized distance, and then we use a modified Demons algorithm in order to register the whole population. This was an original registration method that was then applied to a population of 173 patients coming from a national study, JET2. And what we ended up was in a sub-region, so repeated on 118 patients, and we ended up in a region which was more predictive of rectal toxicity, and this region was easily reproducible in different patients. So this region is these results suggest that this region is probably related with rectal toxicity, and we can think on transferring this region towards a new patient in order to reduce the toxicity at the planning step. In the urinary toxicity, we tackle the same problem. The issues with the urinary toxicity is that if it's associated with the bladder presents a very large interfraction deformation. Moreover, the urinary toxicity presents different symptoms and grades. It can involve different structures, not only the bladder, but there are evidence suggesting that the urethra can be involved in urinary toxicity. So to go with the first problem of interfraction deformation, in the PhD of Richard Rios, we developed machine learning methods in order to learn from this bladder deformation based on intraoperative CT data. What we showed is although the bladder is highly deformable, one part of the bladder is rather fixed, which is the basis. And indeed, as a consequence, we didn't improve the prediction of toxicity based on the pH. So we had to go through a new voxel-based method, as what Eugenia Milona did in her PhD. It was to propose a new 3D voxel-wise analysis, but only customized for urinary toxicity. And she proposed a workflow which was implemented for correlating those in urinary toxicity. As you can see here, the core is the same as for the rectum, but also includes block for predicting different symptoms. Particularly, it includes also the registration, the segmentation of the intraprostatic urethra in order to investigate whether the urethra was compromised in urinary toxicity. And it's what she did, and she showed that indeed there are different. She found 5 symptoms related to regions associated with those, and indeed these subregions for incontinence, retention, dysuria, and hematuria were more predictive than those to the whole bladder. And this is a very, very important result that led us to propose ways of implementing that in the clinics. So, as a conclusion of all the methods, in our works, we went beyond the DVH and we show ways to exploit the data to predict toxicity and find subregions that can be used in the plan. So the question is now how to transfer these subregions to the planning for a single patient. Well, we think that there are two steps before doing that. The first is an external validation to see whether these subregions are valid in an external data set. And secondly, is whether this is technically feasible. To answer to the first question, so Eugenia went to Italy in collaboration with the Istituto Generale di Tumori and compared with the same data set, the subregions that she found in the bladder and urethra with the results based on those surface maps. And she found that 3 of the subregions were found. So there's a slight advantage of voxel-based method in order to explore the whole body. And the second validation was an external validation with the same subregion. She went to Australia for a couple of months in order to test on the radar trial 476 patients that were treated with a conformational radiotherapy, who received it between 66 and 74 grades. What she found out is that 3 out of the regions were found as predictive of urinary toxicity, not the 5, but 3 of them. You see that they're important. And the rectal subregion was not confirmed. This may be explained because of the technique. The subregion was found using IMRT, and the data set, standard data set for validation was using conformational radiotherapy. But it was an important result that pushed it forward or validated the intention of going to the clinics. Now, the second question, how to bring the subregions to the clinics? Well, in a project, interlabex between the CAMI and COMI labs, after lodging a patent on that. We developed a tool which is able to import these subregions into the PES. So once you have the organs delineated, the subregions is also imported into the PES, and then a planning can be performed using both, using either the organs or using the subregion. And this is also very nice tool that was used in a pilot study with 60 patients, where retrospectively the different plannings were performed with subregions or without subregions, and these plans were compared for this population using this tool. And what we show is if the planning was performed with the subregions, we have the subregions, we take the subregions into account, we achieve a reduction in probability of rectal toxicity up to 20%. So in conclusion, of this first part of the work, we can see that we propose a new framework, which is very original for studying 3D toxicity. And it involves 3D spatial dose comparison via non-registration, which we propose new registration methods, segmentation as well. This allows us to define subregions or organs or explore the relationship with the dose and toxicity. It improves the prediction, and moreover is that these subregions can be imported in the planning. There are some issues still to solve. We are working together currently on those problems, such as the fact that planning dose is not representative of the delivered dose. That correlation between dose and toxicity doesn't mean that this dose is causing producing this effect. We need to reproduce on larger cohorts, not only in CRT, but in other populations treated with different radiotherapy systems. We have to combine this data of dose. Dose is not the only responsible of toxicity. We can be other biomarkers. And we have to define which dose volume constraints in the TPS should be implemented. Also, as a conclusion, we have in this work co-directed 5 PhD students, more than 10 masters, 4 postdocs and engineers. We have been funded by different projects, CAMI and COMIT Labs, Interlabex. There is currently a maturation project in order to bring that to the links with the clinic, with the industry. This European project that I coordinated and I started this year, it's ERA-PERMED project with partners in Italy and Spain. And the idea is to bring this concept of subregions also to the clinics. I will speak about this project later on. It's a fruitful work with more than 10 journal papers, conference papers, patent, software tools, been divided to several talks, and it's an international network we built with Australia, and Italy, and Spain. Well, let's switch to the second part of the works, mainly in recurrence. Prediction of the recurrence following 2 approaches. The first is the radiomics and then the silico simulation. This part is lighter. I decided to show not only the methods in depth, but mainly the contribution and the main results for the sake of equilibrium between the works. So the first question is the use of radiomics workflow as a predictor of recurrence, and this is basically based on quantitative analysis of medical images. Well, to this end, in the works in clinics of Kemara Neb and Frederic Comandor and Ricardo Gutierrez, we've been working in developing methods for extracting features from images, the MR. So the idea in this study, Kemara Neb, we collected data from cohort of 70 patients with a follow-up of 5 years using 2 different MR, and we developed the lineage were performed manually by expert radiologists, and then we developed a large set of tools for extracting features from these images. We followed all the international documentation in terms of international works, in terms of standardization. So we developed first order features, second order features, texture hierarchy features, geometric gradient features, Gabor filters. We used a lot of panoply of different features developed in Frederick's PhD, and to build then a model based on different alternatives. We use random forest. We started with SVM, random forest, or well, registration, random forest, in order to ensemble learning, in order to build a model. Well, what we have shown is that indeed some hierarchy features were found as predictive of recurrence 5 years. However, these approaches based on data are very limited in interpretability. We don't know why the entropy of a gradient or this feature in the concurrence matrix are related with recurrence. So one of the problems as well of this data-based approaches is need a large amount of data, and we need external validation. And very often these data are unbalanced, which means that the number of events are not represented, higher enough to draw clear conclusion. So as opposed to that, we have been developing in collaboration with another team in the lab, the team, the mechanistics models, where the idea is trying to understand the biology concepts, the biology interaction between cells and irradiation, in order to propose a model of cell proliferation and tumor growth, and in response to predict recurrence. So this work was initiated in a project, Cancer Program TEST, with Jan Vera as a product. But we pushed really forward this field with the thesis PhD of Carlos Sosa Marrero, who defended 2 days ago, and where he really developed the whole framework for using this model. The idea was to have a better comprehension of the biological mechanisms, some model that can be explainable. We can explore and simulate different dose tumor configurations, and also in the future, the idea is it will allow us to improve the personalized planning via in silico tests. So what is the idea? The idea is to have cells, in silico cells. We have defined 5 different cells: healthy cells, tumor cells, damaged cells, endothelial to supply blood, to supply oxygen via the blood, and dead cells. And we built a model with that, and we implemented the 4 more important biological mechanisms involved in tumor growth, namely the oxygenation, as you can see here, where every blood cells supply oxygen, the tumor growth, as you see in the right, the division of healthy cells, and also the angiogenesis, which is the growth of VEGF, is a protein who favors the growth of new vessels. And the interesting part in this, and the challenging part in this, is that those are mechanisms arising at different scales, time scales. We can speak about milliseconds in the oxygen supply, while in the terms of tumor growth, we're speaking in terms of hours or even days. And the challenge was to propose an integrated model taking into account this difference in time scales and in space. So we used a library proposed in the lab a few years ago called M2SL to come up with this complex model, which takes into account everything. And also we implemented the response to irradiation, where the irradiation is at
the same time killing the tumor cells, so irradiating the healthy cells. And based on a linear quadratic model, we can see that we can simulate the response to the rat. Well, this complex model was huge in terms of parameters, which complicates observability, identification. And what we proposed afterwards was, in collaboration with the team as well, was to run a sensitivity analysis using a screening method like Morris, where we run more than 70,000 simulations using for that in silico synthetic tissue built from histopathological samples, and where we simulated the tumor growth or the process of tumor growth and response to radiotherapy to see whether some of these parameters are important or not in the output. We came up with a huge model based only on 18 parameters, and where we showed that the most important mechanisms affecting the output are the oxygenation and the division of cells, the time division of the cell cycle. Well, we proposed a paper that was published this year in Section 1 Medical Engineering. So we use this model. As you can see here, this model simulates everything. It simulates the number of cells, the radiation, and how the cells are dying, and then the tumor, once the radiation stops, when the tumor starts growing again. And by using this in silico model, we can simulate different fractionation as well. So we compared thanks to our work with Pierre Fontaine, with the PhD in collaboration with Switzerland. And we performed a comparison with radiology. So by using the same patients as in the first cohort before, we performed a first prediction. And then in a second step, for each one of the patients, we built a digital tumor, an equivalent tumor representing the patient. So it's an avatar of the patient. And on this tumor, we simulate the radiotherapy treatment, and we use the density of cells at the end of the treatment as a predictors, and we compare both. And as you can see here is the difference between the two populations, patients with recurrence and patients without recurrence, is significantly different in some areas. And what we found also is that the predictors using the tumor are higher. The predictions are higher than with the radiology. So this opens a very nice perspectives in terms of prediction using model-based approaches, which are also explainable. We demonstrated the utility of a library in terms of which integrates different formalisms and different space and time scales, which is the big challenge. However, there is a big problem in terms of observability that we have to cope with. As a conclusion of this second part, we can see that it's a good prediction we can achieve with radiomix. However, the model-based approaches improves the prediction, and we are achieving promising results. But the tumor response is very complex. We need to, for example, immunotherapy system. We have problems of observability and identification of parameters. If we want to push that platform of prediction of simulation to the level of tool for time. And doing this work, we co-supervised 4 PhD students, 2 postdocs, and 1 clinical research medical doctor who was doing clinical research with us. We have research funds from different organizations, Cancer Texan, FHU Texan, la John Bretagne, France Life Imaging. And we have published different journal papers as well, international collaboration. And to finish with this, the last part of the work has been in MRI planning. So we are facing the problem of limitation in the use of CT in the planning, because because there are large inter-observer variability, the volume, slow estimation of prostate volume. The prostate tumor is invisible in the CT, and the tumor CT is not assessed. However, unlike this, the MR is very rich in information, as you can see here for the same patient. So the question that we are answering is how to combine, how to include the MRI within the plan. In Frederic Commander's PhD, co-directed with Anton Simon, well, we proposed some methods in order to answer to this question, how to introduce the MRI in the plan. So the idea was extract characteristics from the MRI, delineate the prostate, and via registration, trying to transfer all the regions of the MRI to the CT and use it in the plan. So for the first one, that part of characterizing, we developed the methods for tumor detection, for accuracy prediction, and for targeting, using the same features that we used before for prediction of radiomics. So from MR, we were able to propose probability maps showing the places where the tumors are. And in order to assess the Gleason score, we used it for validation group of patients that went through prostatectomy. So we registered the histology to the MR, and we validated the Gleason score with the probability maps that we obtained from MR. So it was a preliminary study with only a couple of patients, only 8 patients. Here you see part of these results. So for each patient, we were able to validate where the tumor were located, and also to validate the Gleason. This work needs to be extended to a large population. I think what is a few years ago. So it's the next step. So for registration, we also proposed in Fredric's PhD a method based on the contours. So we have contours from the CT, from the MR, and this registration method proposed was based on, it was published years ago as well, was based on the normals, on the collinearity of normals between these contours in CT and MR. So the problem is still the difference. C'est la session qui acabó. La session. Hein? Ah, j'ai mis la fin à 13h. Ah oui, c'est ça. Si ça coupe comme ça. Ah, il faut quoi? Il faut la mettre large. Il me manque 2 minutes encore. Je suis à 43. Et il me reste le projet, la conclusion, voilà. Donc, l'idea was to... Ah, allô. S'il doit venir. Ah oui, bien. So the second aspect, well, to cope with that is to provide the electron density from those calculations directly. So this was developing to compute the dose. We were developing the Axel's large on PSD. And the idea was to generate from MR synthetic CT. It was done in collaboration with Australia. So the idea is from MR, we produce a pseudo CT, and on pseudo CT, we can compute the dose. So Axel developed methods based on machine learning, and mainly in using the GAN, so the generative adversarial networks, deep learning. And he proposed several, well, how to use the GAN to do that, and how to bring that to the dose. So he compared the dose computed with different approaches. And particularly, it's interesting that he showed that the GAN offers a very nice performance in terms of production of synthetic CT. This work has been co-directed as well with Jean-Claude Nunes in the lab. And this is some of the results of the GAN. So you can see the MR, the CT, the real CT, and the pseudo CT, synthetic CT, using the GAN. So the results are very good. And one of the problems that we are trying to resolve in that Chirac PhD is how to describe the errors, because the errors in this generation of CT are not homogeneous everywhere. So the idea is to show a method, or to propose a method that is able to highlight the difference, the errors in the generation of the CT through the cartography. So the idea is to bring all the population to a single template and to perform voice analysis in order to show that some methods are more performant in some regions and why, trying to explain that, and then to come up with methods, proposed methods for quality control. So in resume, the same scheme, resume 4 pages students, 1 postdoc, 5 journal papers, and the project. So the project is trying to answer to 2 different questions. The first one is the patient stratification. So we stratify the patients using, what does it mean? Personalized therapy means things to try to identify a group of patients which are more likely to have toxicity or recurrence. So we're going to do that through the toxicity models with included prediction, but also including multimodal data, mainly biological data. We are going to go also to the in silico simulation in order to predict the recurrence. So the idea is to stratify some patient to show that he's more likely to have risk of toxicity. And the second aspect is once the patient is identified, how to improve the planning for him. It means that we have to define sub-regions specifically for him and to use the MRI also and to customize the target. And the idea is to better define the PTV, the prostate, and also the structures at risk to be spared. Particularly, I want to just explain very quickly what is going to be done in the future with that. We in the toxicity model, so we are supported, as this is how to disappear. We are going to be supported by, once you have the sub-regions defined in the first part, we are going to develop that in an European project in partnership with Spain and Italy. And the idea is to bring these sub-regions to the clinics by first externally validating the existing sub-regions and then trying to test to find new sub-regions, introducing deep learning in order to segment them automatically, trying to find ways to transfer that to find the constraints to be applied to the sub-regions and go to a real personalized planning. This is basically the workflow of the project. I don't have time to go through all the steps. The idea is to take the existing sub-regions, validate them externally, develop deep learning segmentation methods in order to bring it to the TPS. Then compare different radiotherapy system, and then to develop tools for automatically introduce them into the plan. Well, I don't have time to do that. And at the end, I think I'm going to skip that. I have to skip the idea also is to push forward the idea of the digital patients, to have a patient and simulate on him all the possible fractionations in order to optimize the grade and the number of fractions for this particular patient in order to optimize the grade. So as a synthesis, we have developed methodologies in image processing, segmentation, registration, data fusion, population analysis, voxel-based, machine learning, and modeling. We applied all these methods, personalized therapy in terms of prediction of recurrence, toxicity, improved target delineations. We transferred that to the clinics. We developed a patent tools. We are in a maturation project. We are in a European project trying to looking for transferability. We have, in terms of scientific outputs, are peer review papers, conference proceedings, abstract, international collaborations. Several PhD students, engineers, postdocs, all of them have contributed to this work. We enriched international collaborations with Australia, Italy, Spain, and Colombia. And we have been funded with several grants. Particularly, I want to mention the European project, which will fund this work for 3 years. Finally, well, I am participating in different scientific activities. I am part of the International Summer School in Biomedical Imaging organized every 2 years in Saint-Jacques-de-la-Mer. I am also co-chairing actually the ESB 2023, which be held in Cartagena de Indias in Colombia. So I'm part of the I chair of the conference, and that's it. That's all the people. Voilà, je suis à 50 minutes. Comment? Comment? Je suis à 50 minutes. Bah, c'est la première fois que je l'ai fait. Hein.
Ouais, bah, c'est bien.
C'est la première fois que je suis.
C'est super. Hein. C'est riche, c'est très dense.
C'est très dense, oui.
C'est très dense. C'est super. C'est énorme, hein, tout ça. Hein.
C'est énorme, oui.
Non, mais c'est énorme aussi tout ce travail. Hein. Tout le travail.
Ah, là, la présentation?
Non, ça démontre tout ce que tu as fait.
Ah oui.
C'est énorme.
Oui, mais c'est beaucoup d'années.
C'est
pas un an, c'est 2 ans, c'est tout ce qui est fait ici en France. C'est structuré un peu.
Non, mais c'est vachement bien. Tu pourrais dire que tu as focalisé sur les interventions des présidents.
Oui, attends, je note ce que tu dis, parce que c'est important.
C'est frais pour pas que tu perds trop de temps.
Oui.
Déjà, tu as mis combien 50 minutes?
Comment?
Tu as mis 50 minutes.
Oui, je suis à 50 minutes.
Ouais. Et puis tu vas quand même vite, hein, c'est un rythme.
Ah bon?
Ben, à la fin, tu vois le projet.
Oui, c'est pas les temps.
Tu avais combien de dépôts normalement? Tu en as rempli une ou deux, tu n'as pas parlé d'une ou deux, non?
Qu'est-ce qui se passe?